All right. Hello and welcome to another physics video lecture. Today we're going to be talking about impulse. Now, impulse is like the best friend to a term that we've already seen, okay? And its best friend is momentum, which, if you remember, momentum is when a mass is in motion, okay? Anything that's moving has momentum, all right? Momentum can be thought of as how difficult it is to stop something from moving. If something has momentum, it is moving, it is very difficult to stop. If you are a comics fan, you think of the Juggernaut. The Juggernaut has like unlimited momentum, all right? The equation for momentum is P, which I know that's weird, that's momentum, is P. It's because M is already for mass, all right? So momentum is equal to mass times velocity. All right. Any mass that is moving has momentum. Okay. The bigger the mass, the bigger the momentum. The bigger the velocity, the bigger the momentum. Okay. And we saw this last class. Pretty straightforward. The units are pretty straightforward. We take kilograms for mass and multiply them by meters per second for velocity. And again, you can kind of think of it as the opposite of inertia. Inertia is how difficult it is to change something's velocity. And it's only based on its mass. I don't love that definition, but it helps some people. So what is impulse? Impulse is when you change an object's momentum. When you think of impulse, you probably think of those two football players from the opening slide, right? When you feel an impulse, your current momentum is going to change, all right? And that's exactly what we see here. Now, the trick with impulse, okay, is that there are not one, but two equations for it. Okay, so I'll show you what I mean here in a second. The first one, okay, is very simple. If you change your momentum, well, you got to think, well, what are you changing? Well, you're not changing the object's mass, right? You're changing the object's velocity. So here we have impulse, which again is weird. It has to be like its friend momentum. Instead of an I, we use a J, okay? And the reason we don't use an I is because later you'll see we use I for current. So anyways, this is all in your equation sheet, but we use J for momentum, all right? And it equals the mass times a change in velocity. That's what a change in momentum is. Do you speed up? Do you slow down? Did you hit a wall, right? Whatever it is, you're changing the object's velocity. Now, in order to change something's velocity, we've seen before, you have to accelerate the object. That's what a change in velocity is. And the only way to accelerate an object, okay, is to apply a force. Oh, I should get back to this. Here, the units are kilograms times meters per second. They're exactly the same. Kilograms is mass, meters per second is velocity. Okay? But like I said, impulse comes from a force. So the other way to calculate that is if you take the force that's applied and multiply it by the time, you also get impulse. Okay? The unit for this is force times time. Well, force is newtons, time is seconds, so we can use newtons times second. It is important to remember, okay, that these two units are equal. We can actually play around with this. Remember, a newton is kilograms times meters per second squared. So if you mess around with the units, you actually do get these two. And again, without diving too much into it, because we don't need to bog ourselves down, these two units are equal to each other, as are these two equations. Because look, they both equal J, okay? And if two things equal the same thing, well, guess what? They all equal each other. So this is the first time we've really seen this year, but it's not super mind-bending. This is actually how it's written down in your equation sheet, okay? Impulse equals force times a change in time, which equals mass times a change in velocity. And the trick to doing these problems is to remember that any two of these equal each other. If they just give you impulse, force, and time, just use those two. Maybe they just give you impulse, mass, and the change in velocity. Just use those two. Maybe they don't say anything about impulse. Then here's where it gets fun, because you can set these two equal to each other, okay? So we're going to see a couple of mathematical examples of that in just a second. But the one thing that I want to talk about with impulse is a really important notion, and it's the notion of how you can safely change your velocity, okay? So if you want to change an object's velocity, you really only have two choices, okay? So like let's say, for example, let's say you're driving down the street, okay? You're in a car, that car is going 60 miles an hour, okay? If you want to stop that car, that's an impulse. If you want to go from 60 miles an hour to 0 miles an hour, right? Well, there's really only two ways of going about doing this. Number one, you can do it with a lot of force over a short period of time, meaning you slam the brakes and you go from 60 to 0 in a very short time. When you do that, you feel a huge force, right? You literally feel yourself moving back and forth, right? Or if you're polite, you use a very small force over a very long time. This is like slowly tapping the brakes, okay? And here's where we see that force and time equation come into play. Another way, okay, that you can think about this is that if you want to make the force of an impulse less, right? Well, what you got to do is you got to increase the time. What do I mean by this? If a mass goes from 60 miles an hour to 0 miles an hour, the impulse is set, right? Mass times a change in velocity. Whatever that impulse is, if you're going from 60 to 0 miles an hour, you're going to feel a certain amount of impulse. Okay, but there's two ways you can feel it. Either A, you can take a very long time to come to a stop, and if you do that, you feel a very small force. So again, for example, you're going 60, you slowly tap the brakes, and over a long period of time you come to a stop, and you don't feel a lot of force. Or, with that same amount of impulse, you can use a huge force over a very short period of time. That would be slamming on the brakes. Again, you're going from 60 miles an hour to 0 miles an hour, but here you're feeling a huge force because the time is very small. So remember, all three of these are going to be equal to each other. It's just a matter of how much force you use over what period of time. And we actually use this to our advantage in tons of applications, okay? For example, the thing that keeps you safe in car accidents is an airbag, right? Why does an airbag keep you safe? Why would you rather have your body hit an airbag than the steering wheel? Well, it's because the airbag is soft. And when you hit something soft, it slows you down over a longer period of time. And when you have a bigger time, you feel less force, right? When you hit something hard, you go from moving to stopping very, very quickly. And when you do that, you have a very small time, you feel a huge force. This is the same reason why if you're boxing, you want to wear boxing gloves, right? If you're punching something, you'd rather punch a pillow than a wall. Why? Because when you punch a pillow, it's big, it's soft, it's airy, and it causes your hand to slow down, right, over a long period of time, okay? Same thing with the boxing gloves, right? If you punch a wall, your fist goes from however fast it's moving to stopping immediately. The pillow, it slows it down. Same thing with those attenuators on the side of the highway. If you've ever seen those big piles of sand for runaway trucks, okay, the reason that you'd rather hit a big pile of sand or hay or pillows or anything soft is because it brings you to a stop over a long period of time, as opposed to hitting a brick wall, which brings you to a stop immediately. And that's why hitting a brick wall causes you to feel a huge force, where hitting an airbag can extend that time and make the force you feel smaller, thus hopefully saving some lives, okay? Similarly, when we talk about cars, I like to bring up this idea of old cars versus new cars. A lot of people think that old cars are safer because they're stronger, they're built out of steel, right? And don't get me wrong, I love old cars, okay? And it is true, old cars are harder to break. If they get into an accident, they're more likely to come out of that accident still more intact because the car is stronger. New cars are built out of plastic, right? And aluminum and these like softer materials. But there's a reason why, okay? When an old car hits a wall, okay, the car is rigid, okay? Which means when it hits the wall, it comes to a stop, boom, immediately, okay? Now, the car is strong, so the car is gonna look pretty good, okay? but you are inside the car, and because you come to that stop really quickly, you gotta remember, when you come to a stop quickly, in a small time, you feel a big force. So in that old car, you're gonna feel a huge force. The reason why new cars are made of softer materials is because they have these things called crumple zones. You can think of like an accordion or like a soda can being smushed together. When a new car hits the wall, what happens is it hits that wall and the whole car crumples in. And what that crumpling does is instead of coming to a stop, boom, all at once, it smushes itself in and it's like hitting that pillow. So in this case, you have a longer time, so you feel less force. And as much as I love old cars, the reason that I would rather be in a new car in an accident is because even though the car is gonna look a lot worse after the accident, I'm gonna look a lot better. All right, let's do a couple examples real fast so you can see how to use these three equations. All right, we got Smitty running down the road. He's got a mass of 90. As always, make a chart. So we got 90 kilograms. He speeds up from 7 meters per second to 10. These are velocities. We have an initial velocity or a starting velocity of 7 meters per second and a final velocity of 10 meters per second. All right, for this one, we are just gonna use our normal impulse, right? So impulse is equal to mass times a change in velocity, okay? Which means mass is gonna be equal to the mass times the final velocity minus the initial velocity. You're gonna hear me say this a bunch. Whenever you see this triangle, that means change in, okay? And change in is always final minus initial. Always, always, always. Okay? So, plug your numbers in. Impulse is equal to 90 times 10 minus 7. 10 minus 7 is 3. I'm just gonna cross that out. So we have 90 times 3. I should have my calculator over here for good measure. I'm pretty sure I know what 90 times 3 is, but let's just double check. Always use a calculator. 90 times 3 should be 270. There you go, 270. So that's your impulse. So you could say J equals 270 kilograms times meters per second, or you could say Newton seconds. They're equal, they're the same. You ever heard the phrase 6 of one, half a dozen of the other? That's because 6 and half a dozen. There you go, you get it. All right, number 2. Here we have a Volvo, sturdy car, all right? This Volvo has a mass of 1,200 kilograms. And again, as I always say, stop the video here, see if you can solve this one. Did you get an answer? Let's see what you got. It experiences an impulse of 24,000 Newton seconds. Okay, so we got an impulse of 24,000 Newton seconds, which is a little easier to write. If it started at rest, initial velocity is 0, because it started from rest. How fast is it now traveling? What is its final velocity? All right, mass, initial, final, impulse. We're gonna use the same equation, okay? So again, impulse equals the mass times the final velocity minus the initial velocity. Remember this here, this is your change in velocity, okay? That's what those two equal. Always where you finished minus where you started, okay? How much money did you make? Well, how much money did you end up with? Subtracting by how much money you started with. That's the change in your amount of money that you made, okay? Plug your numbers in. J equals 24,000 is equal to our mass, 1,200, times our final velocity, which is what we want, minus our initial velocity, which is 0. Well, this is fun, and actually quite easier than you might think. Anything minus 0, VF minus 0 is, I don't care, right? So all we really have here is we really have 24,000 equals 1,200 times VF. So to get VF by itself, this is multiplication. So I'm going to do the opposite of multiplying because I want this by itself. I'm going to divide both sides by 1,200. And go back to our calculator. Anybody got this number? 20. It was going, or it will have a final velocity, J equals 20 meters per second. Oh, did I say J? What am I doing? VF. Come on now. Our final velocity is 20 meters per second. Okay? That's what that impulse does. Did you get 20? Bet you did. Good job. All right, so let's look at the other side of that equation. Let's look at that force and time side of the equation. All right, so we got a bowler. Okay, we got a bowling ball. This bowling ball is 6 kilograms. Kilograms is always mass. It's rolling at 12 meters per second. All right, so that is our initial velocity. If it hits a wall and comes to a stop in 0.4 seconds, that is our time. Also, it hits a wall and comes to a stop. If it stops, that means we actually know our final velocity. Final velocity is, you guessed it, 0, because it came to a stop. How much force is exerted on the wall? So we want to know what the force in this situation is. All right, so we got a lot going on here. We got mass, we got a change in velocity, time, and force. All right, so what we remember from before is, remember, we knew that the impulse equals force times time. It's a change in time, but time's always changing. I never really understood change in time. Like, that's what time is. It's changing all the time. So it's force times how much time passes, times mass, times final velocity minus initial velocity. All of this equals J. Now notice there's 3 equations and 2 equal signs. I don't see an impulse anywhere, nor is the question asking me for impulse. So in this case, we actually are ignoring that part of the equation. Okay? It's an impulse problem without the impulse. It's crazy, right? So now let's just plug our numbers in. Our force is what we're looking for. That's going to equal my time. Oops. It's not going to equal. It's going to be multiplied by my time, which is 0.4. That's going to equal the mass, which is 6, times the change in velocity. My final velocity is 0, minus my initial velocity, which is 12. Okay? Now, as I always say, if you have straight math, just do it. So the first thing we have to always do, right, PEMDAS, is the parentheses. 0 minus 12, okay, gives me negative 12. If you don't remember how to do that, put it in a calculator. But I'm telling you, 0 minus 12 is negative 12. In fact, I'll take the 3 seconds to show you. Plus it'll give me that number. Okay, so we have 0 minus 12. I hit enter, and I have my answer, which is above, which is negative 12. All right, so now I have 6 times negative 12. So I'm going to go like this. 6 times, watch this, second answer, negative 12. I love that trick. That gives me this side of the equation, which is negative 72. So now I have negative 72 over here. I have force times 0.4 here. I'm going to keep this up. Can you guys see this? All right. I want to get force by itself, so I have to move the 0.4. This is multiplication. So I do the opposite, and I divide both sides by 0.4. 0.4 divided by 0.4 is 1. Here, I'm going to go again and hit enter, and then I'm going to take my second answer, which is negative 72, and divide it by 0.4. And that gives me my answer, which is negative 180. So the force that this bowling ball feels is negative 180 newtons. Why is it negative? Well, because the bowling ball is going this way, right? And it stops. So the only way to stop something that's going this way is to exert a force going this way. And since it's an opposite direction, remember, negative is just a direction, all right? So this is a negative force. Negative just means opposite direction. All right. Last but not least, all right, here's this. And last but not least, we have a train. Love trains. Train speeds up from 10 to 20 meters per second. Awesome. So 10 is our starting or initial velocity. 20 is our final velocity, 20 meters per second, that is, over the course of 30 seconds. Well, we got ourselves a time. In order to do this, a force of 300,000 newtons is applied. So I know my force, 300,000 300,000 newtons. What is the mass of the train? We're looking for mass. All right, guys, so we're using that same equation as before, right? We have impulse is equal to force times time is equal to mass times final velocity. That's initial velocity. Again, nothing about impulse. We got nothing about impulse. So again, we don't care about the impulse here. All we care about are these two sections. So here we know the force is 300,000 times the time, which is 30. And that's going to equal the mass, which is what we're looking for, times the final velocity, which is 20, minus the initial velocity, which is 10. Again, it's some numbers, but all I'm doing is plugging in the numbers that I wrote down into my equation. And this is pretty straightforward. Step number one, do your basic math. So I have 300,000 times 30. So we'll start there, clear everything. 300,000 times 30. That gives me 9 million. All right? And then over here in parentheses, I have 20 minus 10. All right? So I'm going to bring this down. This side, I have 9 million. 1, 2, 3, 4, 5, 6 equals my mass times 20 minus 10. 20 minus 10 is 10. And as you can see now, we're back to a pretty basic problem. We want mass by itself. So we got to move the 10. This is multiplication. So we divide both sides by 10. 10 divided by 10 is 1. And we have 9 million divided by 10, which hopefully you can take a guess at what that is. But even if you can't, you go enter. Answer divided by 10. And that gives me my answer, which is 900,000. So the mass of this train is 900,000 kilograms. So you're going to see different versions of this. There's a lot of ways to play around with it. It might just give you the force and the time and ask you to find impulse. That's easy, right? It's the same thing that you did with the mass and the velocity. You have the time, you have the force, find the impulse. All right, guys, that is it for today's lecture. As always, use this, write down the notes, copy down these practice problems, work through them, and if you hit a speed bump along the way, email me, find me at tutoring, and I'll help you out. All right, guys, have a great day.